And then today we're going to switch and focus a little bit more on the acceleration due to gravity at different locations, right? Those things are different. Agreed? Force and acceleration are different. The gravitational force is how much something is pulling on something else. The acceleration due to gravity would be how fast something is falling, right, when it's being pulled by gravity. So they mean two different things. So what I want to look at here is these kind of steps by steps of this derivation of the equation. We know this equation. That's the one we got yesterday, right? That's Newton's universal law of gravitation right there. So we're going to start with that. We're going to take that equation and we're going to manipulate it or derive it, right? That's another word for it. We can derive this equation. All we're going to do is substitute the mass of the Earth in for one of the masses, okay? Because when we're talking about the acceleration due to gravity, we've got to be talking about it on a planet, right? Most of the time, Earth, right? If it's a different planet, you would use the mass of that planet in there, okay? But all we do is substitute in the mass of the Earth for one of those m's, okay? So now it just reads me times m2 over r squared, right? That's the only difference here, is that's me. Now we're going to take one more step, and we're going to substitute what we know. Fg is usually equal to mass times the acceleration due to gravity, right? That's how we've always solved for Fg in the past. So we're just substituting mass of my object times acceleration due to gravity. That would be my Fg. Does that part make sense? That substitution? Okay. And then if you look carefully, you're going to have an m2 on both sides. And so when we've got an m2 on the numerator and both sides, what do? Right, we can cancel that out. And so that leaves us with our final equation here. Little g, or acceleration due to gravity, equals big G times mass of the Earth over radius squared. Okay? So this allows us to solve for the acceleration due to gravity at different heights, basically, right? We talked about how the acceleration due to gravity on the top of Mount Everest might be slightly under 9.8, right? I think we're actually going to get a problem like that a little bit, like the next problem, okay? We're going to be able to examine that a little bit closely, okay? But that's an equation that we're going to use. Remember that little g is measured in meters per second squared, right? It's an acceleration due to gravity. Usually at the surface of the Earth, it's 9.8. Other places, it's not. So if we would plug in all the numbers we know about like the radius of the Earth, the mass of the Earth, and big G, this number would come out to 9.8, right? That's how that number was really kind of calculated. So let's go ahead and try one here. I've been talking about Mount Everest, and this is the problem we're going to get into for it. What is the acceleration due to gravity on the top of Mount Everest? And then it tells us the height here. 8,848 meters above the Earth's surface. When it says acceleration due to gravity, we're not solving for Fg, right? We're solving for little g, okay? So if I put in my little g equals big G mass of the Earth over r squared. Okay, I'm going to attempt to draw something here. Okay, here's Mount Everest. Okay, that's all you get. It's as artistic as it gets. Okay, 8,848 meters. Obviously not drawn to scale either, but there it is, okay? When we solve our problem, what do we want that radius to be? What does it have to be, the distance from what to what? Good, exactly. From our object, so from our peak of our mountain to the center of the Earth. So all the way to the center of the Earth it has to go. Okay, so we know the radius of the Earth equals 6.38 times 10 to the 6th. That's one we got yesterday. And so since we want this total distance, what are we going to have to do to those two values? We're going to have to add them together. Okay, so you can go ahead and do it now. You can wait until you plug it into your equation. I'm probably going to go ahead and do it now. Radius, I'm going to take 6.38. We stored that in our calculator yesterday, remember? So if you do alpha r, if you stored it in there, alpha r plus 8848 Don't round this, because then it's still going to look like 6.38 times 10 to the 6th, right? It's going to be 3, 8, 8, 8, 4, 8.
Why do we add it?
Because when we plug in the radius to our equation, it's always got to be from our object to the core of the Earth. So Mount Everest is 8,000 meters above, and then we've got to take into account the radius of the Earth. We want the total distance there.
So there's going to be like barely any difference.
Yeah, not a lot of difference there, right? But we can't just round it to 6.38 times 10 to the 6th, because then it will look like there's no difference. So we do need to keep that full number in there. Okay, so here we go. Little g, that's what we're solving for. Big G. Tell Willie what big G is. Good. 6.67 times 10 to the negative 11th. We have the mass of the Earth, 5.98 times 10 to the 24th. That's another value that was given. And then the radius we just solved for, 6, 3, 8, 8, 8, 4, 8. And then, Pat, what do I need to do on the denominator?
Square it.
I need to square it. Okay, I need to square it. We have to make sure that radius number gets squared, and it's just something that we're going to forget pretty often.
Under M, who squares under M?
I don't know what you started as.
Me either.
Okay. 9.77 meters per second squared. Very good. So, are we going to float away at the top of Mount Everest?
Yep.
Right? I don't think so.
Jump high enough.
I don't think so. I don't think we're going to feel a difference. Right? I don't think we're going to feel a difference.
Why am I not getting the same answer as Noll?
All right, if two objects have equal masses and they sit 1.2 meters apart, find the masses of the object if the force of gravity between them is 0.035. We had one pretty similar like this on the homework last night. Okay, so I want to walk through what we did to help that. All right, force between them. So that's not little g. This is FG this time. 0.035 newtons. The radius is 1.2. And then we don't know either mass. But we do know that M1 equals M2. Right? Because it says their masses are equal. So we don't know what they are separately, but we know that they equal each other. Okay? So if I plug into my equation, 0.035 equals big G M1 times M2 over R squared. Okay. I'm going to go ahead and rearrange here until I'm kind of left with that M statement, and then I'll go from there. So I'm going to go 0.035 divided by G.
It's going to be a fairly big number.
Yeah. And then I'm going to take that times my 1.2 squared. And that gives me, yes, it does get like 7.556, that number?
Yeah.
Okay. So I'm going to go ahead and take that 7.56 times 10 to the 10 to the 8th equals M1 times M2. Okay, are we okay with that math so far?
So you just divided by big G and then multiplied by 1 point.
Yep, and make sure you do that 1.2 squared first. Don't try to plug it in without parentheses because it might do order operations wrong. Okay. So once I'm to that point, then what do I do to find the masses? Do I divide by 2? I square root, right? This is what we had to talk about last time. If M1 equals M2, then essentially what we have is M times M, which does not equal 2M, it equals M squared. Okay, and so that would equal that number up there, and so I need to square root both sides to get that. So that leaves me with a mass for each M1 and, oh, that's not really an answer, and M2 equal, I think, 27,488 kilograms. Agreed? Is that what we had when we square rooted that?
What am I calculating?
So here we go. This one says, if one object weighs twice as much as the other, and they sit 0.85 meters apart, find the masses of each of the objects if the force due to gravity is 0.15. Okay. If one object weighs twice as much as the other. I'm going to give you a minute to get what you want written down, and then we're going to start working through this together. Okay. We know that our radius is 0.85. The force of gravity is 0.15. And here's what we know. One object weighs twice as much as the other. So what I'm going to do is I'm going to say M1 equals 2 times M2. Okay, can you guys see what's probably going to have to happen here? Mm-hmm. We're going to have to do a substitution to get these two variables to be the same. Okay, so let's go ahead and look at our regular equation. FG equals big G times M1, M2 over R squared, right? That's what it really looks like. If I go put in the numbers, 0.15 equals big G. I don't have M1 or M2, but I do have this term right here that I can substitute in. So what's that going to look like? Am I going to be left with M1s in my equation or M2s in my equation? M2s, good. Okay, so instead of M1, I'm going to substitute that out, and I'm going to say 2 M2 times M2 over 0.85 squared. Okay, does that part make sense how we did that? That substitution? The one we did on the homework was equal masses, so they had just m squared, right? But now we've got 2m squared.
I thought there was one we had like take the Earth times the.
Oh, yeah, you're right. Yeah, but that one, they gave us some mass. This one, we don't know the value of either of those m's. All right, so we're going to solve for that. So let's do the math here. Divide over g, 0.15 divided by alpha g. That gives me a big number. So my g's are canceled. I'm going to take that times my radius squared. Okay, after I've done that, I'm going to multiply by 0.85 squared. That gave me a value of 1,624,812,594. Right, it gave me this big number. Agreed? And that is setting up to equal what? 2m2? 2? Is it 3m2? Is it? 2x times x is 3x? Yes. It always works better when I say it with x's. I don't know why. This happens every year. It's really 2m2 squared. Right? 2x times x would be 2x squared. Right? So now I'm going to divide by 2. Divide by 2. And then I will have to square root both sides. Okay, and so what mass really does this get me? It's not both of them, it's just one of them. Which one is it? It gives me M2. That equals 28,502. And so then what would M1 have to equal? What would M1 have to equal then?
1,401.
No, go back and look here. M1 equals 2 M2. So it's really twice as much of that. Twice that. So 57,005 kilograms. Those are tricky. Okay, those are tricky. Try to get this one started on your own. Any ideas about how we're going to get this started? a man's weight, sorry, I clicked ahead there. A man's weight is the same as Fg, right? We're not talking about the mass changing. We're talking about his weight changing. So here's our equation. Mass of the earth, mass of the man, over radius squared. We want to know at what distance from the surface of the earth is the man's weight reduced to 1/4 of his original weight on the surface of the earth. Okay. What's another way that we could solve for Fg? Mass times 9.8, right? Agreed? Okay. That would give us what his mass is on the surface of the earth, right? But we don't want to know anything that's happening on the surface of the earth. We want to know 1/4 of his original weight. So we're at a point here where we just need to go like times 0.25. Right? Because I don't want to know his full weight. I want to know 1/4 of his weight. And then at this point, it really doesn't matter how much he weighs because the m for the man is going to end up canceling on both sides. Do you see how you can manipulate the equation to get it to work like that? So now we're really at a point where we can just go 0.25 times 9.8. That gives me 2.45 equals big G times mass of the earth over r squared. We know big G and mass of the earth, so we're like ready to go to solve now, right? We didn't have to know any information about him. We just had to know how far away or how much of a ratio they wanted that mass to be. So from there, I'm going to divide G over. So let me give myself some more room here to work. Oops. Okay, divide G over. So 2.45 divided by G gives me 3.67 times 10 to the 10th equals mass of the earth over r squared. So I know mass of the earth, but I don't know r squared. What do we do in our variables in the bottom? Switch them places. So that's going to leave me with r squared equals the mass of the earth. So alpha m divided by that 3. Okay, I think that value gives me 1.63 times 10 to the 14th when I do that division. Mass of the earth divided by 3.67 times 10 to the 10th. Yes. Am I moving too fast or are we doing okay? Got that same thing? Okay. So from there, how am I going to get r by itself? I'm just going to square root. Okay, and so that leaves me 1.27. I'll round it right there. Oh, no, I can't round it. Okay, yeah. 1275940 meters. Whew! Okay, that's a lot of math, right? A lot of calculator work. But now I want you to think about one thing. Is this the final answer? Bingo. We got to subtract out right now. This guy might be here, right? So the radius that we have is that full distance. We really only want to know this distance. So we've got to subtract out the radius of the earth. Okay, so minus 6.38 times 10 to the 6th. Right. It really, you almost get exactly that, right? 6.38 times 10 to the 1, 2, 3, 4, 5. Oh, yeah, it is to the 6th. Okay. Okay. Orbiting of satellites and planets. So these are things that are putting both together. We're putting our uniform circular motion with our laws of gravity to really explain planetary orbits, right? Why does the moon orbit in that circular path, right? We talked about circular motion first, and then we're combining it with the laws of universal gravitation. So, when things are moving in uniform circular motion, that means that they are always at the same height above the Earth, right? The Earth is a circle, okay? Believe it or not, it's a circle, right? We're not flatlanders, okay?
Yes, we are.
The Earth is a circle, so it's always going to stay in the same height above the Earth. So we've got this circular orbit happening. If I wanted to find the speed of the satellite that's in circular orbit, I'm going to combine these two equations, basically. There's a lot of math between these two equations, but I narrowed it down to what you need at the end, right? Here's what our equation comes to. After we do a bunch of manipulating of our equations, this is for satellites specifically. So on your equation sheet, I would make a separate little section for satellites and put these two equations in there. Okay, this gives us the velocity of the satellite, and then the next one gives us the, what is that? What's capital T? The period of the satellite. Good. Okay, so both of those give us information, but they are satellite specific. So I would make sure you write that on your equation sheet, that they are specifically for satellites. Okay. Again, there's a lot of math and combining of equations that went into making these. I left that part out because basically we just need the equation. Okay. I'm not sure that we need to go through too many problems with satellites because it's really just plugging in the numbers, getting your answer out, right? I want to make one note here about this equation. I will say, when you go to solve this and you divide by 2 pi, you have to be very intentional in your calculator. If I hit 10 divided by 2 and then I hit the pi button, just like that, 10 divided by 2 pi, what's my calculator going to do? It's going to take my number divided by 2 and then it's going to take it times pi, right? That's 15. 10 divided by 6.28 is not 15, right? So you're going to have to go 10 divided by parentheses 2 pi, or you're going to have to do 10 divided by 2 divided by pi. Okay, does that make sense? Really intentional about when you bring that over that you're not doing your order of operations wrong. Okay, because it will take it times and then it will divide. It's not going to put in parentheses if you don't put in parentheses. Okay, I just wanted to make that note because I know that'll be something that we go over. And then if you need to do the cubed root of something, like if I wanted to solve for r, do you know how to get to that point? Cubed root in your calculator is under math. And then you can scroll down to number 4. And then that would be your cubed root of something. Okay, so it's under math and then you scroll down to 4. Or you could take it to the 1/3 power, I think. Okay. All right, very good.